In this video, we're going to be focusing on Objective 2.4, Structures of Metals and Alloys. So the learning objective states that we're going to represent a metallic solid and or alloy using a model to show essential characteristics of the structure and interactions present in the substance. So, in 2.1, we talked about the different types of bondings, and we only a little bit touched on what a metallic bond would be. So this objective is let's focus on just metallic compounds, especially talking about what an alloy is. We're going to be focusing on two different types of alloys, and you'll need to know the difference between them. So metallic bonding, like we mentioned in 2.1, can be represented as an array of positive metal ions, so cations, surrounded by a delocalized valence electron, which we call that sea of electrons. So depending on what the charge of the cation is, that will tell us how many valence electrons would be in this sea of electrons. So a +1 cation, there would be 1 electron per atom. If it was a +2, we would have double the electrons within that amount of atoms. So unlike ionic compounds joining metals to nonmetals, metallic bonding joins a bulk of metal ions. And so the strength of the metallic bond actually depends on 3 things. So like I was just saying, the number of electrons that become delocalized. So AKA, how many valence electrons are we talking about? And then whatever the number of electrons that become delocalized, that's actually telling us the charge of the metal, or we can say the cation. And so here, these go hand in hand with one another. I do just want to note, when it comes to transition metals specifically, it's very hard to figure out what the charge is, because they are considered variable charges. They don't have fixed charges. And so you can't just look at, the fact that it will have a 4s2 for that first row of the transition metals. 4s2 meaning that it has 2 valence. Here it's going to have multiple charges. For example, copper can be copper 1 or copper 2. Iron can be 3 or 4. I think it can sometimes be 2, but regardless, you can't just look to see where it's on the periodic table to figure out what the charge is. And then lastly, the size of the metal and cation. Now, when it comes to the size in the transition metal, it is kind of hard to see what the general trend is. Go based off what the general trend of atomic size decreasing left to right when we go across, but we can't really use nuclear charge in this sense to explain that because of their valence electrons. All right, so let's talk about the 2 different alloys now. And in case we don't know what an alloy is going to be a metallic substance composed of 2 or more elements. And so we do have 2 types. Our first one is called interstitial alloy, and we have substitutional. So let's talk about interstitial. So here, this is one of the atoms are much smaller and will fit in between larger metal atoms. So here, one of the atoms added are much smaller. In general, when we look on a periodic table, what elements are going to be smaller? And when I talk about elements, I'm talking metal, non-metal, metalloid. Here, the smaller atoms are generally be non-metals and will fit in between the larger metal atoms. Please don't get confused with non-metal and anion. Here, we're not having anions in this case. In that case, that would have been an ionic compound. Here, I'm just talking about a neutral nonmetal. Here, these smaller atoms, they're going to fit in the holes between the metal atoms. Here, I'm going to just scroll in real quick. You can see this interstitial alloy in my picture. You can see the orange is representative of carbon, and the gray circles would be iron. So here you can see these little carbon atoms are fitting in between the holes or the pockets of all the iron. Now, please note, when it comes to alloys, you're generally going to have one element that is going to be in the higher percentage, higher abundance. So here, iron would be our metal, but to make an iron type alloy, we can add carbon within those iron metals, making that the interstitial. This example, actually, fun fact right here, is steel. I do want to add this because we're adding non-metals to an interstitial alloy. You generally will see hydrogen, carbon, and boron. That doesn't mean that another element can't fit in those holes of those pockets, but here generally you'll see those three. Next one, a substitutional. This is the atoms added to the metal, again the one in the higher abundance, have similar size / radii. So they replace existing atoms in the arrangement. And so here, I'm going to scroll and look at this picture. Here's substitutional. Nickel is going to be our more high abundant metal in this case. And so here, what they ended up doing for this type of alloy is they remove some of the nickel atoms and will replace it with a metal of the same size. Here, copper was able to replace the other nickels. This actual example in real life is called brass. Now, looking between these two, interstitial and substitutional, the interstitial is going to be stronger compared to the substitutional that is weaker. One thing that we can use a justification for is the fact that those carbons are fitting in the holes of the already iron atoms gives it a stronger effect, stronger in the sense that it's harder to break. It's going to be not as malleable because those atoms aren't going to be able to move as much as the other one, the substitutional, where you can see a lot of open pockets or space. All right, so what I would like for you to do right now is pause the video and try this out yourself. So let's talk about this example. So to the right, we have two examples of alloys. One is going to be an alloy of tungsten with carbon, while the other is copper and tin. Label the two types of alloys and create a key to label each type of atom. So here, tungsten is going to be element W on the periodic table. It's in the transition metals. Carbon is C. It is a non-metal. Copper is Cu, tin is Sn on the periodic table. So the fact that right now I am leaning towards starting with the one that's carbon with the tungsten, because that is going to be the one with the smaller atoms fitting in the gaps between the metal atoms. So here, B is going to be my interstitial alloy. Here, this is its tungsten and carbon. Carbon is going to be the small yellow atoms. Tungsten will be our, I guess, gray, blue, large atoms. So you can see those carbon atoms are just fitting in between the other tungsten atoms already in that arrangement. That leaves us with a substitutional. So here, this is going to be our copper and tin. Now they're relatively going to be the same size. You will notice that the yellow is actually smaller than the blue-gray color. So here, looking at our periodic table and going kind of based off what we know about energy levels and the way atomic size decreases left to right, I would say the tin is the blue-gray atom, while the copper will be the yellow atom. They're relatively the same size, but you can see tin is actually just a little bit bigger, and that's definitely because it's going to be found in energy level 5, while copper will be found in energy level 4.